Welcome to chapter 21, which is the last chapter in the book. So, in this book, we will discuss the popular operating system Windows 10. So, we'll start with the history, the design principles, the main system components. Then, of course, Windows 10 has some facilities that make it work like a server. So, we'll discuss terminal services and fast user switching. And then we will go to more traditional file system components such as the design the more traditional OS components such as the design of the file system and networking subsystems and the programmer interface that is provided to program to do systems programming on Windows 10. So the objectives are that we will explore the principles upon which Windows 10 is designed and the specific components are also designed. We will look at detailed explanations and illustrations, describe the interface that is available to application programmers and important algorithms that are implemented. So, going to the history, so Microsoft has been around for a long time now, at least for the last 35 years that I have been seeing Microsoft products. So, they used to have a DOS based command line operating system, which of course changed with DOS 6, which had a GUI of some sort, a graphical user interface. And DOS 6 was released in the 92-93 time frame. But in 1988, they decided to develop a new technology based on a graphical user interface that would have supported both the OS/2, which was the predominant IBM operating system at that point of time for PCs, and the POSIX APIs, which were Unix based APIs. So originally, NT was supposed to use the OS/2 API, but of course, during development, the API changed and it became a separate operating system with its own application programming interface. So, because they realized that this is something that could become big, so Windows 3 was born. And then, of course, many versions of Windows came, right? So, Windows 98, Windows Millennium, XP, Vista 7, 8, 10. And in fact, as we speak, I am recording this presentation on Windows 11. Many older versions are still in use, so some of them are not supported by Microsoft anymore, and the more important security updates in many are missing. So Windows 10, well, what does it bring to the table? So it is the latest state of the art 32 and 64-bit preemptive multitasking operating system with these being its key goals. So it is portable in the sense it runs on a large number of devices. It has security. It has many security extensions. It is POSIX compliant in the sense that it is compatible with many of the programming level abstractions that Unix has. It, of course, has extensive support for multiprocessors and it is extensible. Furthermore, given the fact that Windows is used in a large parts of the world, it has a lot of international support and it is compatible with almost all. So there is a huge amount of backward compatibility. So it's compatible with a very large number of old MS DOS and old Windows based applications. So it primarily relies on a microkernel architecture where we have a small microkernel, which is like the core of the kernel. And quite similar to Linux, we have a bunch of modules which are kind of added to the kernel at runtime. In addition, Windows, like Android, has a large app store from where we can buy a lot of Windows applications. Windows does provide a Windows desktop bridge to run older binaries, right? Quite similar to what we have seen in Linux, the namespace concept. But this is basically to run binaries compatible with older version of Windows. The Hyper-V virtualization support, so there is a native virtualizer quite similar to KVM, and a lot of features for multi-user services, distributed services, remote desktops, and so on. So these were things that Linux used to have, which drew many people, including myself, towards Linux in the early days. But then, of course, things changed in the sense that these features came into Windows and now they are quite easy to use. So, in terms of design principles, we have both attribute based and claim based. So, we will see what these are in later slides. But for every object, so Windows, so basically in Linux, if you would recall, almost everything is called a file, right? So, it could be a device is called a file is called a file. Things like pipes and semaphores are also called files if they are stored in the file system. So in Windows, everything is called an object, and every object has an access control list. So there are, you can specify this in great detail who's allowed to do what on the object. And furthermore, for every user, we can specify capabilities, and these capabilities are also represented internally as integrity levels. So we look at both these mechanisms of security. There is a lot of support for encrypting files, data, and communications. Along with that, we can do a lot to mitigate most of the common security exploits which are common as of today. So they do address space layout randomization, for instance. So as we have discussed, what is commonly or normally done to mount a buffer overflow attack is that we inject some code into a process by basically overflowing a buffer or overwriting part of the stack, and either we execute that or we try to change the code section. So we need a very accurate idea of which code lies in which part of the address space. So this can be randomized. So if this is randomized every time a program runs, it will be very hard for the attacker to guess which piece of code lies where, which is quite easy. So all addresses are specified as an offset from, let's say, the stack pointer or from some other pointers in the heap or other pointers in the data and code section. So we can effectively randomize the address. Then, of course, data execution prevention, in the sense we mark all data pages as non-executable. We guard the control flow, so we ensure that nobody can tamper with the code. In addition, particularly when we are dealing with driver code, the driver is signed by a trusted vendor. This basically helps Windows trust the driver, and it ensures that any third party driver which does not have certain security guarantees and is not subsequently signed meaning digitally signed, it is not allowed to run on Windows. Then we have the device guard option, which provides a lot of fine grained control over what exactly the device driver can do in the system, which parts of the kernel it can access and which parts it cannot access. So then, as we have discussed, extensibility is a very key idea in the Windows kernels. In the sense, if this is the basic kernel, given that the kernel is used for a large number of applications, there is support for doing a lot. So it does support a layered architecture. In addition to regular procedure calls, it supports RPCs, remote procedure calls, and also advanced local procedure calls. So we'll not be discussing every single detail of what these are. It's beyond the scope of the lecture, but you can definitely Google for these. So in terms of portability, Windows 10 has a lot of advantages. It has moved from regular desktop hardware to embedded hardware. It's primarily written in C, C++, as are many other operating systems in the space. But similar to other OSs, the processor specific portions are written in assembly. And the design of the kernel is quite like this, that there is a generic part of the kernel, which is of course not dependent on the platform. And the code that is dependent on the platform, right? So of course for x86 you would have one, and let's say if Windows runs on ARM, you'll have another. So this is known as an hardware abstraction layer or HAL, and this is loaded in dynamically into the kernel as a DLL. So this part is platform dependent, and this code often comprises, often is made up of assembly routines. So Windows 10 has many more interesting aspects, facets, and features. One of them is reliability. So Windows 10 uses almost all the security mechanisms that any hardware provides. So given the fact that Windows is so popular and so widely used, many times hardware vendors and Microsoft, they work in tandem. So it uses hardware protection for virtual memory and all other software protection for OS resources. It, as we have discussed, is compatible with the POSIX standard, and it can compile and run any code which is compliant with POSIX, which basically ensures at a high level Windows code and Unix code. Of course, forget about the libraries, but otherwise the code as such is quite compatible. So in terms of performance, Windows has extremely efficient IPC mechanisms where Windows subsystems and processes can talk to each other via a very high performance message passing mechanism. And then we have preemption of low priority threads, which enables the system to very quickly respond to external events and interactive events because it's meant to be a graphical user based system. So interactive events have a high priority. And it has been supporting multiprocessing for a long time, so this is nothing new. What is interesting is that Windows is now like a de facto standard operating system all over the world. So it has extensive support for different languages and different date formats, time formats, and so on. So this is known as support for internationalization. Then we have energy efficiency, which means for portable devices, we have a lot of features that Windows provides, such as the dynamic tick feature, management of processes, activity monitors, and battery monitors, and methods to take the system to standby if it's not being used. So, particularly for mobile devices, so Windows is designed to run on them. Energy efficiency is a very important criteria. So, the Windows 10 architecture, so we have discussed some parts of it. It's a layered architecture. For the lowest part is, of course, the hardware abstraction layer. And then we have the kernel. And then we have a part known as the executive. So, we'll talk about these uh, over the next few slides. So, Windows, like Linux and like many other operating systems, not everything runs in the kernel. Many subsystems actually run with user space permissions. So, basically, also there are modes to emulate different operating systems, other Windows based operating systems, and there are a lot of protection subsystems which provide security functions. Right, so basically, they operate in both the user space and kernel space to ensure that at no point of time security is breached. So the depiction of the Windows 10 architecture would look something like this, the hardware being the lowest level, and then we'll have a hypervisor. So basically, the hypervisor is a layer above it if Windows is being used as an hypervisor. So this would mostly be a type 2 hypervisor. And but of course, the way that this is positioned, in this case, it is acting as a type 1 hypervisor because the hardware abstraction layer is on top of it. And then we have the hardware abstraction layer, as we have discussed, is just a lot of bundles of assembly code to connect with the kernel such that the kernel's code can remain the same, but the code for different targets will nicely be captured and abstracted out in the hardware abstraction layer. So then we have the kernel, which is the core kernel. So this is a typical microkernel based design. So then we have the executive. So the executive over here still runs in kernel mode, because as you can see, this is the kernel mode user mode boundary. But the executive is not a part of the core kernel. It has many parts that run with kernel permissions, but can be loaded and unloaded on demand. One of them is the IO manager, which provides a bunch of services. It provides services for the file system cache, and device drivers. So the device drivers, so Windows supports hundreds, thousands of de- devices. It would be quite impractical to have the code of all of those devices within the kernel itself. It would be extremely impractical. So what is more practical is to actually keep them as loadable modules and load them. Then we have other parts of the executive to manage objects, security, processes, power, configurations, local procedure calls, where of course the kernel provides some support, plug and play devices, and memory. So all of these are features which of course rely on the kernel but are not part of the core kernel, at least the way Windows views it. And that is why they are a part of this unit called the executive. Then there is also a part of the windowing subsystem, which in Windows at least it does run partially in kernel mode as opposed to Linux. So in this case, we have device drivers for graphics cards and a part of the window manager which runs in kernel mode, right? So in Linux, of course, a large part of it runs in the user mode, which in a sense is good and bad. First is that it decouples the kernel from graphics intensive tasks, but also the other thing is that it makes it difficult for doing things that involve graphics. For example, the moment you plug in an external monitor, Windows very nicely mirrors the display or extends the display. This used to be quite hard in Linux. The main reason being that the communication between the kernel and the graphics subsystem was not all that great. So once we come to the user mode, which is this part, we have a lot of DLLs. So of course, the Windows NT DLL is one of the main DLLs, which gets mapped to many processes, right? So basically, to a very large number of processes, quite similar to the standard C library. This DLL code also gets included, but there are also many other subsystem DLLs that get included into the code of many other processes. So in this case, we will have different subsystems similar to Linux, which actually run in user space. So for example, the login shells and the session management shells, everything run in user space. There are many system processes similar to what we had like init in Linux. So we have the login process, the init process, which is the first process which forks the rest. So they again run in user space. And finally, we have services. So in services, we have a print spooler and a services host. So all of these services to also interact with devices, they run in the user space and they naturally talk a lot to the kernel, but at least there is a part of the process which runs in user mode, because also they don't have a lot of priority and occasionally they need to talk to the kernel. And then of course we have regular user applications, right? Along with the kernel based user applications, we have regular user applications who are the ultimate users of the system, and they also and they, needless to say, have to incorporate some system DLLs, because it's quite similar to the standard library in C++, where you have to include boilerplate code for you know initializing the memory map of a process, exiting a process, and so on. So it's quite similar to Windows. The names may be different, but the basic methodology or the way it works is quite similar. So in terms of the system components, we have looked at a layered system of modules where different modules have different privileges. And then we have the kernel and user mode, as we have seen. The kernel mode over here, the user mode over here. And then, of course, we have different virtual trust levels, which is implemented in the virtualizer part of the OS. So, a VTL or a virtual trust level enables a virtual secure mode. So, it enables a normal world, which is VTL 0, and a secure world, which is VTL 1. Within each world, we could have both user modes and kernel modes. So, the secure world, which is VTL 1, will have a secure kernel and a secure executive and a collection of other smaller programs known as trustlets. All right. So the key point is that the moment we have this Hyper-V based virtualization, so Windows itself becomes a guest which is running on top of the virtualizer, and then we can specify different rules for the guest. So we can either allow it to run normally, which would be VTL 0, or we can make it to run in a secure manner in which its interaction with the hardware will be curtailed and monitored. Right? That's the key idea. And needless to say, just above the hardware, which is the bottommost layer, it will run in a special processor mode, which basically means that as far as the processor is concerned, it will be the layer with the largest, with the maximum privileges. So this is known as a VMX root mode on Intel. And this is where the Hyper-V hypervisor, which is the hypervisor component of Windows, will run in. And this will create some sort of a hardware based normal to secure world boundary, where, of course, the Windows OS is running as a guest. And just below the guest, we will have a virtualization layer, right, which will determine the way that the guest OS runs, in the sense whether it will run in the normal world or in the secure world. And below that, we have the hardware itself. So now let's come to the kernel. So the kernel is clearly the foundation of everything. So it's the foundation for the executive part, is the foundation for the subsystems. So the kernel is never really paged out of memory. So it is something that remains in memory, and its execution is never preempted. All right. So the kernel stands tall and stands supreme. So it has four main responsibilities in Windows. The first is thread scheduling. So the scheduler is one of the key components, so to speak. Then it does interrupt and exception handling. Low level processor synchronization, so provides synchronization facilities for tasks. And its job is to essentially manage the boot process and also recover after after a power failure. Right? So it is essentially scheduling, interrupt handling, synchronization, and recovery after a power failure or booting. So the kernel of Windows is written using C++, an object-oriented language, which uses two kinds of objects. So everything is an object in Windows as compared to Linux where everything was a file. So we have dispatcher objects and control objects. So dispatcher objects control the dispatching and synchronization of threads and processes, and this is done primarily via events. So events are like alarms, you can set them. Mutants, mutexes, semaphores, threads, and timers. So basically, dispatcher objects control the execution of threads and processes. Then we have control objects. So control objects don't look at the synchronization or coordination aspects, even the dispatcher objects look at the synchronization and coordination aspects of processes and threads. So control objects are mainly for doing higher level control tasks such as asynchronous procedure calls, i- interrupts, managing interrupts, and so on. Power notify, power status, and process and the profile objects. So they are the control objects. So this is again, kind of a fuzzy boundary. But the key point is synchronization and coordination is dispatcher because it has everything to do with dispatching tasks. And control objects is control tasks basically, which is everything to do with the way that tasks interact and interrupts and all of that. So it is also possible to create enclaves So which is something on the lines of what we were discussing, that we allow valid signed third party code. So third party code is code written especially by device driver manufacturers. So it is valid and signed, and so they are given some additional privileges when they are running on the processor. So they can perform crypto calculations with the built-in instructions that are there. So what we need to focus most on the kernel is the way that these objects are created and the way that they interact with other parts of the operating system. So let us now look at some key aspects of the kernel. So the first is processes and threads. So every process has a virtual memory address space, similar to way the processes have virtual memory spaces in other OSs. Information with regards to a base priority, which is its process execution priority, and an affinity with one or more processors. So the same way in Linux, we can specify a CPU affinity, which basically says that this process should preferably run on which CPU. Something similar can be done on Windows. In this case, quite similar to Linux, threads are the unit of execution in the kernel's dispatcher, where every thread has the following state. It has a priority, an affinity, and some accounting information with regards to how much it has executed. A thread can be in one of 8 states. So Linux had fewer states, but Windows are more states. Initializing, ready, deferred ready, standby, running, waiting, it's in transition, and it has been terminated. So each thread will naturally have two modes of execution. So in Linux, we had a user mode thread and its mirror kernel mode thread. So in this case, we say it's the same thread, but it has two modes of execution, which is tantamount to the same thing, user mode and a kernel mode. But again, for all practical purposes, these are two separate threads with their own respective stacks because they run in different memory regions. And the job of the kernel thread is to perform whatever the user mode thread is asking the processor to do. So it will process interrupts, exceptions, everything else, system calls, and so on. For the kernel scheduling, it uses a 32 level priority scheme where higher is the number, higher is the priority. So the priorities themselves are divided into two classes. The real time class contains threads with priorities from 16 to 31, the most important. And then, of course, you have the regular threads whose priorities range from 0 to 15, which is low priority. So the logic behind the priority scheme of Windows 10 is like this. The key aim is to give a very good response times to primarily interactive tasks. This is because Windows is a is by and large a desktop based operating system, even though of course nowadays Windows Server is becoming quite popular. So this is why in Windows good response times for interactive threads are heavily prioritized. So furthermore, the priority scheme also enables IO bound threads to keep the IO devices busy as much and as far as possible. And so this should not be compute bound threads then soak up whatever spare cycles are there, which means the spare cycles that are there after all the high priority and real time threads have executed. Whatever spare cycles are there, they are taken up by background threads. So scheduling can occur when a thread enters, right, the ready or the wait state, which basically means that the moment a thread becomes ready, we will see if it can be scheduled. Or let's say a thread is running and then it invokes an IO operation or a system call or something. Then the CPU becomes free, so we can then make a scheduling decision. Or when the thread terminates. Of course, the thread terminating is not a special event as such. So every thread would basically terminate by calling the exit system call. or I mean something equivalent in Windows. So that is when we will have to look at scheduling the next thread. Sometimes within an application, we can change a thread's priority or CPU affinity. In that case, again, it is possible to look at scheduling some other task. So real-time threads, needless to say, are given preferential access to the CPU. But again, Windows 10 does not guarantee that a real-time thread will execute within a particular time limit. So it's not a hard real-time system. Instead, it tries to schedule real-time threads preferentially. So it is basically a soft real-time system. So let us now look at some Windows interrupts. So the interrupt levels are defined like this, where higher the level, higher the priority of the interrupt. So level 31 is known as a machine check or a bus error, which for obvious reasons has the highest priority because if the machine fails, then clearly we need to take a look at that first, and after that is a power failure. So these two are clearly the most important because something immediate has to be done. Next is an inter-process notification. So this mechanism is there in Linux as well. It's known as an inter-processor interrupt. So what happens is if there are two cores in a system, one core can send an interrupt to another core. This will pretty much load the OS on that core. This is very important, particularly if there is something of immediate importance that needs to be done, like flushing requests from the cache or the TLB or something like that. 28 is a timer interrupt. This has a high priority because we really do care about interactivity. From 27, 3 to 27, these are relatively lower priority interrupts, with 3 to 26 being the traditional hardware interrupts. 2 is again special. It's a deferred procedure call. So this is something similar to a bottom half in Linux in the sense we say that, look, I will execute something later. And so this is a very, very low priority interrupt. And the same is also with 1, where we make an asynchronous procedure call. And when the return comes, it comes via an interrupt, right? So these are some asynchronous function call mechanisms which are important, but which have a very, very low priority. Now, coming to the kernel and particularly trap handling. So, when exceptions and interrupts are generated by, should be software and hardware respectively. In the sense, exceptions are generated by software and interrupts by hardware. Then, at that point of time, the kernel provides mechanisms to handle them or deal with them. So, exceptions that cannot be handled by the trap handler or the interrupt handler are sent to the exception dispatcher, which is the default trap handler of the kernel, and then it does something. So based on the kind of interrupt, either it terminates the process or it does something. Similarly, we have an interrupt dispatcher in the kernel. So its job is basically to look up the interrupt table and figure out that who is handling this interrupt. So for example, let's say if it's a keyboard interrupt, then the interrupt will be sent to the keyboard device driver. Or let's say if it's an internal kernel routine, that kernel routine will be called. So of course, the interrupt code in Windows. One thing is that because Windows is not an open source operating system, a lot of internal mechanisms are not really known. But it is widely believed that any operating system should have or should primarily rely on a top half and bottom half kind of mechanism to keep to handle interrupts. And then, of course, the Windows kernel does have a lot of spin locks that reside in global shared memory to achieve mutual exclusion when it comes to multiprocessors. And we have discussed a lot of this, we have discussed this issue in great depth in the Linux chapter, where we argued that it's not a good idea for sensitive pieces of code like the top half of an interrupt handler to actually mm, acquire kernel locks. So something similar must be happening in Windows, but given the fact that we are not privy to the source code, we can only conjecture about this. So Windows 7, as we have discussed, uses the term objects for all of its services and entities. We have an manager which is generic in the sense it generates an object handle regardless of the type of the object. Checks security in the sense it checks if, let's say, the requester has adequate credentials and the permission to uh, access the object, and it keeps a track of which processes are actually working on the object. In the sense if the object is deallocated or deleted, then which processes will get affected. So this information is there with the kernel. With the kernel. So there are some standard generic interface kind of functions for manipulating an object with a set of methods. The methods are namely create. So create stands for create an object. Open, close, delete, query name, parse. So again, parse if some arguments are being sent to the object, and security calls. All of these calls, by their name are obvious. So there is no need to further elaborate. So the Windows executive, the executive part of the kernel, something that we were seeing earlier, it allows almost any object to be given a name, right? So it could be a permanent name, so something as we have seen as a named pipe in Linux, or could be a temporary name. So it could be like an anonymous pipe in Linux, but an object can be given a name. So of course, some objects are not given a name because they are already named in a certain sense. Like for example, a process which has a PID, a thread which has a thread ID, and some other object types. So furthermore, object names are structured like file path names in MS-DOS and Unix. So they have a reasonably elaborate name. And furthermore, pretty much like Linux and Unix, Windows 7 implements a symbolic link object, which is similar to symbolic links in Unix, that in a sense allow multiple nicknames or aliases to refer to the same file. So the same way that we have symbolic links in Windows and we have symbolic links in Linux, the idea is the same. In Linux, of course, multiple files, symbolic links to files refer to actual files. In the case of Windows, since everything is an object, they refer to objects. The same way we get a file handle in Linux or Unix, a process in Windows 10 gets an object handle by essentially creating an object or opening an existing object. It can furthermore also something like a hard link in Linux. It can receive a duplicated handle from another process, or it can even inherit a handle, which is an object handle in this case, from a parent. And each object, as we have discussed earlier, is controlled or protected by an access control list, which gives a detailed list of all the users and all the groups, right? All the groups being more important, uh, that can actually modify the object or access the object. So every object, as we have seen, has a set of things that can be done to it: create, open, modify, view, delete, and so on. So who has permissions to do what? So the other part of the executive in Windows is the virtual memory manager. So any modern operating system, which is not really an embedded operating system, has to have support for virtual memory, right? Without that, nothing will work, and something of the scale and size of Windows, it definitely has to have. So previously, the size of the virtual memory that Windows used to support was for 32 bits, well, the maximum is 4 GB. Out of that, the top 2 GBs were reserved for the kernel and the bottom two for user processes. So now, of course, the virtual memory support has become 64 bits. In this case, uh, the, the space is in principle much more. And that is why even page tables, instead of two-level page tables, have become multi-level page tables, 4 or 5 level page tables. And furthermore, there is support for huge pages, where I'll tell you the advantage of huge pages in a second. But it's important to note that the page sizes, whatever page sizes are supported by hardware, Windows 10 would more or less support that. and the page sizes can be 4 MB, 2 MB, or 1 GB. So now you will ask me that what is the advantage of a 1 GB page size? Well, the advantage of a 1 GB page size is that assume we are running some database or some other program, which just wants a large region of memory for itself. So it doesn't want the OS to interfere. The OS is also happy not interfering, and it needs that entire memory region for itself such that it can manage it. Now the point is if the entire memory region is put in the page tables, it will take in a lot of space, right? That's number one. You will have a lot of TLB misses and page table misses, and that will add to the total latency. So this is not really something that we would like to encourage if we really need 1 GB of dedicated space in the main memory. So what we can do is we can treat this as one large huge page and then find a 1 GB chunk in virtual memory and map that to a 1 GB chunk in physical memory. Then within that 1 GB, there will be no page faults and no TLB misses, and life will be fantastic. So that is why such large page sizes are supported, particularly when applications request for them and they would like to manage that memory on their own. This gives them also better performance. So needless to say, any page table manager, including the Windows 10 VM manager, what that would do is it would reserve a portion of the process's address space, the virtual address space basically. And the second step would commit the allocation in the sense it will make a virtual to physical allocation by assigning space in the system's paging files, in the page tables basically. So for a 32-bit addressing, it will be a two-level page table. For a 64-bit addressing, it will be a multi-level page table. So as you can see, there are three levels over here. Starting as a page directory points to a second level page table, points to a third level, and finally that points to a page. So the virtual address translation in the Windows 10 uses several data structures. So let's look at them. So each process will have a page directory at the top that contains 100,024 entries. So let's say 10 bits go over here because 1024 log of 1024 to the base 2 is 10. So each page directory entry points to a page table which contains again 1024 entries of size 4 bytes. So this will again be 10 entries, right? 10 bits. And each PT will point to a 4 KB page frame which is 12 bits. So this is the scheme for a 32-bit addressing system, addressing architecture. But for a 64-bit architecture, we will have more levels. So every page in Windows 10 can either be valid or it could be zeroed out. So note that it is very important to zero out the contents of pages. The primary reason being that if one process has written something, for example, credit card numbers or passwords to a page, and the next process is allocated the same frame, right, the same physical page, it'll be able to read its contents. So that is why before a frame is actually given to a process, its contents are zeroed out. Then there is the notion of freeing a page, putting it in standby mode, right? So it's basically saying whether the page is free standby, whether it is modified in the sense the frame has been modified by the process, or whether it's bad. So bad basically means there is a fault in the memory and the given physical frame cannot be used. So in IA32, which is again the 32-bit version, here we are looking at a three-level paging scheme, which uses the top 2 bits to index into 4 page directory entries. It uses 9 bits for a page directory entry, and these 9 bits are these ones. And then it uses 9 bits again for the page table entry. All right. And then it uses 12 bits for the page offset. So what you have seen is that for a 32-bit addressing system, I can use 2 levels or I can use 3 levels. So it doesn't matter. So of course, more are the levels, higher is the latency, but also more are the levels, higher is the storage in space of the page table, because mind you, for every process, a separate page table has to be maintained. So let's now come to the process manager. So this provides services for creating, deleting, and using threads and processes. So this also maintains issues such as parent-child relationships between processes, process hierarchies, and it also maintains the environment of a process, something that we have seen in Linux as well. And every process itself is represented as a job object. So let's come back to the idea of object. Something similar to Docker, which Linux provides, which is basically a process private view of the file system, including its own files, right? It's like a virtual file system. So Docker container support is provided via job objects. In Windows 10, it is called silos, right? That's what it's called. So now let's come to something that we have alluded to in the past as well, known as the local procedure call facility, or LPC. The job of the LPC is to pass requests between a client process and a server process on the same machine. So when a dedicated LPC channel is created between a client process and a server process, one of three things happen. Right? So not one of three things, but three kinds of messages can be sent, and of course, different mechanisms are used to send the three separate or the three different messages. The first type is suitable for very small messages, which are up to 256 bytes. So in this case, the internal message queue of the port is used for intermediate storage, and basically the entire message is copied lock, stock, and barrel from one process to the other. Because the message is so small, it's 256 bytes, which is nothing but most of the time 4 cache lines, it is quite easy to pick the entire message and just copy it and get done. You don't have to maintain references. The second type is for larger messages where you don't actually copy, but what you do is that you create a shared memory object. You then pass a pointer to the shared memory object, which of course contains the message that the client is trying to send. You send a pointer to the shared memory object to the server. Then again, there is, because as have been indicating earlier, the Windows kernel has special support for graphics oriented tasks. So there is a method called quick LPC, which is primarily for graphics kind of tasks, right? And this is used by the graphical display portions of the Win32 subsystem. So this is specially or specialized for graphics. Now let's come to the IO manager. The IO manager is responsible for several things which are all interrelated, right? So the first is file systems. It implements the file system. Then is the file system cache management. This is because whenever we have a file system, we need a cache also. Because for accessing every file, we don't want to go to the disk. We would like to keep it on the CPU. Then we have network drivers. So basically, and device drivers. So these network and device drivers interact with IO, but entire IO, including files and file system caches, is all bundled together as one super unit in Windows 10. So this also additionally keeps track of which file systems are loaded. So it basically keeps track of file systems, their mount points, and so on. It manages the buffers for IO requests, because if something is being sent to IO device, you have to locally buffer it. It works with the virtual machine manager to also provide memory mapped IO as and when it is required. Manages the cache as we have seen. And furthermore, it kind of manages all IO operations. In the sense, we have looked at synchronous IO and asynchronous IO. This is managed. Timeouts for drivers, in the sense, many times what happens, or what used to happen in old Windows based systems, is that the system used to just crash. There was an infamous blue screen. So most of the time, the code of Windows was not to blame, because Windows code was very rigorously written, verified, and tested. But most of the time, it was actually drivers. So given the fact that the drivers were to blame, there is a need for some executive control on the drivers themselves, and that is why we have timers, and the interaction between drivers and the kernel is heavily monitored. So anytime something is suspected, the driver is terminated. So file IO is quite conventional in the sense the process, let's say, request for IO. It goes to the cache manager to see whether for those IO addresses something is cached. If it is cached, then we get it from the virtual machine manager, right, from the virtual machine system, and it goes via the file system to the process. Otherwise, if let's say the data is not cached, right, so then which means that there is nothing in memory, then of course we have to go to disk or whatever is a storage device that is hosting the file system. It could be a disk or could be a flash drive, doesn't matter. We'll read the data from there and send it back to the process. Windows has a very elaborate security reference monitor. So it has a uniform mechanism which is standardized across a variety of interfaces for runtime access validation, in the sense that when a program is running, it would like to see if it has the permissions to access a certain resource or not, and also to perform audit checks to see if any permissions have been violated. So for this, there is a standardized mechanism. So whenever any given process opens an object handle, we do two things. So one is we check the access control list to find if the process or the group that the user who has initiated the process he belongs to, do they have adequate permissions for opening this object? Another method is that we can look at the process's security token. So it is possible to issue a security token to a process. So in that case, the process, if it has the token and the object accepts that token, it can access that object. So Windows has a plug and play manager as well, because you know almost all the time we keep on plugging in USB devices, headphones, microphones, game controllers, and so on. So it has a dedicated set of drivers which find out which device has been plugged in, locate and load the appropriate driver, and ensure that the device works correctly. And the moment it is plugged out, the driver is unloaded from the system. Furthermore, we access the resources accessed by a device. So this is necessary also to stop deadlocks and to also enforce security. The other important part which is there in the executive is the power manager. So it detects power conditions. So power condition is not just a low battery power or the mains being plugged off. It is also it also tracks inactivity. So if there is an inactivity for a large period of time, it puts the system to sleep or the system goes into hibernation. Then it also manages the processor power for parking the core, in the sense shutting down the core, or for throttling the CPU, which is to reduce the computational bandwidth of the CPU, or for boosting or changing its frequency. If this is in the hands of software, which most of the time nowadays it actually is. So Linux calls this mechanism a governor. So I'm not very sure what Windows calls it. But the main aim of power is to manage the state of CPU and memory for sleep, hibernation, and active conditions, and other devices whose state, particularly with regards to power, needs to be managed. Now let's come to the registry. So registry is an important concept which is there only in Windows. Linux doesn't have it. So let me first tell you what Linux does. So assume we have a software. So there'll be a bunch of configuration information with the software. That would include directories, in the sense where is its home directory, where will it read some files from, its setting, and so on. So for every software, we are essentially reliant on a bunch of files, and if the software is moved, all the files along with also have to move, which becomes quite a hassle. If we want to simplify things, what we can do is that we can create an internal repository that contains all this information. Let us call this a hive. And we have just one centralized data structure called a registry, which has all of this information for every software, and not just that, it has information for devices, it has information for their drivers, it has information for, as we have seen, running software, hardware information, OS information, all the information, configuration information that is there in the system, which includes system information, users preferences, applications preferences, which we call software information, security options, boot options, all of that is stored in a registry, which is pretty much like, it's like an information store for the entire system. So having the registry simplifies things in Windows substantially. Furthermore, the registry is so important that, if the registry gets corrupted, or if you install some software, a virus comes along with it and it corrupts the registry, the system will become quite unstable and things will stop working. This is why Windows needs to create a system restore point before making changes to the registry, in the sense that it converts this, takes the registry, and it takes periodic snapshots. Anytime there is a problem, the previous snapshot is restored. Now let's come to booting. Almost all systems as of today have secure booting, which means that the boot code is there in the BIOS, which is firmware, but its integrity is checked by another small chip. This means this is called the secure boot feature that provides integrity checking, and it also checks the digital signature of all firmware and boot time components. Furthermore, the firmware itself does a built-in self-test kind of thing, a power-on self-test. And if the machine is found, if the firmware is found to be incorrect, the machine doesn't boot. So all of this thing is kind of done by the motherboard and by chips that are a part of the BIOS. So the job of the secure boot process is to also load the operating system, which, as we have argued or as we have explained, the OS is loaded from sector 0, or the starting address of the disk. So this is where the image of the OS is there, and this is where it is loaded. So the machine is hibernating. So the machine can go into hibernation, where basically the CPU is more or less powered off, and most of the other components are also powered off. The state is restored by a dedicated program, winresume.efi, whose job is to again reinitialize the kernel and start many processes. So one process, always the idle process, which is deemed to run if nothing else is running, and a few more processes that we have seen in an earlier slide. This would include the system process, the secure system process, and the session manager subsystem, such that we can at least log into the system. So this finishes the first part of this lecture, where we discuss the file system. Sorry, this finishes the first part of the lecture where we discussed everything about the process manager and the IO manager and the structure of Windows 10. So we will discuss other components in the second part, in the second lecture of this series on Windows 10. So we'll discuss file system, we'll discuss more about the IO and network management parts, and the programming APIs of the Windows 10 operating system. So this current lecture ends over here. See you in part 2.